This is Raghavan, Chemistry faculty from Alforce Educational Institutions. Welcomes you Chemistry e-learning program, session 6th. So in this session, we will discuss about spectra. In the last session 5, so we had the discussion about introduction of spectra, electromagnetic spectrum, and types of spectra. The spectra basically they are classified into continuous spectra and discontinuous spectra. The continuous spectra in which the spectral lines are arranged closely without gap, that is called continuous. The spectral lines are continuous without gap, that is continuous spectra. Example for that continuous spectra is light spectrum. And discontinuous spectra, the spectra in which the spectral lines are well defined with gaps, that is called discontinuous spectra. The discontinuous spectra, next, it is classified into two types, that is emission spectrum and absorption spectrum. Okay, so in the last class we completed up to continuous spectra and discontinuous spectra. Now today let us start in this session 6th spectra, that is emission spectra. Emission spectra. What is that emission spectra? Say for example, electrons normally present in the ground state. Okay, so this ground state electron, by absorbing photon energy, the electron jumps into the higher energy levels. So the electron, by absorbing sufficient amount of energy, the electron get excited to higher energy level. The electron excited to higher energy level. In the higher energy level, the electrons are completely, they are unstable in the higher energy level. So this is during excitation, the electron, by absorbing photon energy, jumps from lower energy level to certain higher energy level. In the certain higher energy level, the electrons being unstable, so the unstable electron de-excited back to the ground state. During the process of de-excitation, the emission radiation is passed through a prism. The emission radiation is passed through a prism, and the dispersed spectral lines are noted on photographic plate. The dispersed spectral lines are noted on photographic plate is called emission spectrum. Once again, when the ground state normal electron, by absorbing photon energy, the electron jumps from lower energy level to certain higher energy level. The excited electrons are being unstable in the higher energy levels. So during de-excitation process, they emits radiation in the form of light. This emission radiation is passed through a prism. The dispersed spectral lines are noted on photographic plate is called emission spectrum. Okay, that is the detailed explanation of the emission spectrum formation. The same thing we can explain in short, that is definition of emission spectrum in short. The spectra obtained from emission radiation, of excited electrons. The spectra obtained from emission radiation of excited electrons is called emission spectra. Spectra obtained from emission radiation of excited electrons is called emission spectra. That is the brief definition of emission spectra. Okay, that is, say, it is first point. And second point, what we can understand, the emission spectra is formed during de-excitation of the excited electron. It is formed during de-excitation of excited electron. Okay, that is the second point we can remember. We should remember that. Third point is emission spectra. How we can recognize the emission spectra? The emission spectra in which bright spectral lines are noted on dark background or dark photographic plate. Bright spectral lines noted on dark background or dark photographic plate. That is third point. Fourth point is emission spectra is formed by hot atomized metals and non-metals. Hot atomized metals and that is hot atomized elements. Hot atomized elements can form emission spectra. So that is fourth point. Once again from the first point onwards. The spectra obtained from the emission radiation of the excited electron is called emission spectra because the light is emitted during the de-excitation process. Okay. The second point is it is formed during de-excitation of excited electrons. It is formed during de-excitation of excited electrons. Okay. It is formed during de-excitation of the excited electrons. Third step, that is third point. The emission spectra in which bright spectral lines are recorded on dark photographic plate. And fourth point, emission spectra is obtained from hot atomized elements. Hot atomized elements, that means they may be metals, or that means atomized means they must be in the gaseous state, and by absorbing huge amount of energy the electrons should get excited. Then during the de-excitation process, so the emitted radiation can give this emission spectrum. That's fine. So this is about emission spectra. Okay. Next one is absorption spectra. Absorption spectra. Absorption spectra. Yes. Absorption spectra in which for example say it is water vapor. Say it is water vapor. Water vapor. Now a beam of white light is passing through the water vapor. The beam of white light is passing through the water vapor. The beam of white light contains 7 colors, that is, say it is Vibgyor. For example, if the water vapor is absorbing yellow colored light, it is absorbing yellow colored wavelength, then the transmitted light is passing through a prism. The dispersed spectral lines are noted on photographic plate. The dispersed spectral lines are noted on photographic plate is called absorption spectrum. This is absorption spectrum. Okay. So the transmitted light contains wavelength of this light. So that is the white light is passing through the water vapor. So water vapor, for example, it absorbs yellow colored wavelength, then it transmits the remaining 6 colors. The remaining light, when it is transmitted, is passed through a prism. The dispersed spectral lines noted on photographic plate, that is called absorption spectrum. That is the first point, that is the explanation of formation of absorption spectrum. Now coming to the short definition of absorption spectrum. The spectra obtained from the absorption radiation. The spectra obtained from the absorption radiation is known as absorption spectrum. That is the first point, as we can write it as definition part. Right. Second point is absorption spectra is formed during excitation of electrons. Absorption spectra is formed during excitation of electrons because the electrons is absorbing photon energy. That is, when they are present in the ground state only, the electrons can absorb photon energy, then the electrons get excited to the higher energy levels. Okay, so absorption spectra is formed during excitation of electrons. And coming to the third point is absorption spectra in which the spectra in which dark lines are noted on, dark lines are drafted on bright background. The dark spectral lines are noted on bright photographic plate. That is the characteristic feature of absorption spectra. Coming to the last fourth point, absorption spectra example. Yes, we can say the same example. That is, water vapor can produce absorption spectra. Okay, this is a concept of absorption spectra. Once again, let us revise all the four characteristics of absorption spectra. The spectra obtained from the absorption radiation is called absorption spectrum. Second point is absorption spectra is formed. It is formed during excitation of the electrons. Third point, absorption spectra consisting of dark spectral lines are noted on bright photographic plate. And fourth point, absorption spectra is obtained from the cold, that is water vapor. Water vapor can produce absorption spectra. That is the concept of the emission spectra and absorption spectra is done. Okay, now coming to the line spectra. Next one is line spectra. The concept of line spectra. It is important. Line spectra is important for IP as well as objective examinations. So the next one is line spectra. Line spectra. So let us say the first point, what is line spectra? That is, say that is first point as a definition. Yes, let us identify the line spectra. Say photographic plate consisting of sharp, well-defined spectral lines. The spectra consisting of sharp, well-defined spectral lines is called line spectra. The spectra consisting of sharp, well-defined spectral lines is called line spectra. And the second point is line spectra. It is the characteristic spectrum of atoms. It is characteristic spectrum of atoms. It is a characteristic spectrum of atoms. Therefore, it is called atomic spectra. Therefore, it is called atomic spectra. Line spectra, it is a characteristic spectrum of atoms. So, therefore, it is called atomic spectra. Line spectra is also called atomic spectra because it is formed by the atoms. Third point. Line spectra is formed during transition of electrons. It is formed during transition of electrons. It is formed during transition of electrons between energy levels in atoms. Yes. Line spectra is formed during transition of electrons between the energy levels. During transition means excitation and de-excitation process. Okay, during transition of electrons between energy levels in atoms. That is third point. Fourth point, source. So, what are the substances can produce line spectra? Line spectra is obtained from hot atomized metals and gases like inert gases. Hot atomized metal atoms and inert gases can also produce hot inert gases. Okay, right. So these are the four important characteristics of line spectrum. Once again, all the 4 points. The spectra consisting of sharp, well-defined spectral lines is called line spectra. This line spectra is the characteristic spectrum of atoms, hence it is called atomic spectra. And this line spectra is formed during transition of electrons between energy levels in the atoms, and line spectra is formed by hot atomized metals and inert gas elements. So this is about line spectra. Next, coming to the band spectra. Next one is band spectra. Band spectra. Yes, the spectra in which the spectral lines are arranged closely. The spectra in which the spectral lines are arranged closely. The spectral lines are arranged closely appears in the form of bands. The spectra in which the spectral lines are arranged closely appears in the form of bands. That is why it is called band spectra. Okay, line spectra is band spectra. The spectra in which the spectral lines are arranged closely appears in the form of bands. Therefore, it is called band spectra. That is first point. Once again, the spectra consisting of spectral lines. The spectral lines are arranged closely packed. Okay, closely packed spectral lines, and the spectral they appear as bands. Therefore, it is called band spectra. Coming to the second point, band spectra is the characteristic spectrum of molecules. Band spectra is the characteristic spectrum of molecules. Therefore, it is called molecular spectra. Band spectra is also called molecular spectra. Molecular spectra. Okay. Coming to the third point, molecular spectra is formed during vibration, rotation, and besides transition of electrons, in the molecules, so that gives molecular spectra, that is band spectra. Coming to the fourth point, it is obtained from source of this. It is obtained from hot gas molecules. Hot gas molecules that can produce band spectra, that is molecular spectra. Once again, let us see the quick revision of all these 4 points. Band spectra, the spectra in which the spectral lines are arranged closely compact, appears in the form of bands, therefore it is called band spectra. It is called band spectra. Coming to the second point, this band spectrum is the characteristic spectrum of molecules, therefore it is called molecular spectra. And third point, band spectra or molecular spectra is formed during vibration, rotation, besides transition of electrons in the molecules. Okay, and hot gaseous molecules can produce this molecular spectra. Okay, this is about spectra, that is continuous spectra, discontinuous spectra, emission spectra, absorption spectra, line spectra and band spectra. Okay, so then after this, before going to take up that hydrogen spectrum, okay, let us discuss about Planck's quantum theory. The next concept is Planck's quantum theory. Planck's quantum theory is Max Planck, scientist Max Planck, scientist, he explained this Planck's quantum theory to explain the nature of black body. To explain the nature of black body, to explain the nature, behavior of this black body, he describes Planck's quantum theory. Okay, what is a black body? What is a black body? The body which is a perfect absorber and perfect emitter of all radiant energy is called black body. That is the nature of the black body. The body which is a perfect absorber, it absorbs all wavelength radiations. Being it is a perfect absorber, it absorbs all frequency radiations and it transmits all frequencies. That is the special nature of the black body. In the universe, there is no naturally existing black body so far, but we can construct or we can imagine or we can assume a artificial black body. A halo metal sphere with a small hole coated inside with platinum black. Coated inside with platinum black. Coated inside with platinum black can act as artificial black body. Once again, let us get back to study the definition of the black body. The perfect absorber and also a perfect emitter of radiant energy is called black body. Okay, so now how to construct a artificial black body, because there is no naturally existing black body at all. The artificial black body can imagine or can be constructed how? A halo metal sphere with a small hole coated inside with platinum black. coated inside with platinum black, can act as artificial black body. Okay, that is artificial black body. Okay, right. Before going to take up the postulates of Planck's quantum theory, so Max Planck explained the relation between intensity of the radiation energy and its wavelength. He explained the relation between intensity and wavelength of the radiant energy. Intensity and wavelength. So let us see the graph plotted between intensity and wavelength. Intensity and wavelength. Along x-axis, let us say it is wavelength. Wavelength, and along the y-axis it is intensity. Intensity and wavelength. Say the first graph. So this is the first graph. Say for example, this first graph is obtained at T1 kelvins. T1 kelvins. Now let us plot another second graph at little higher temperature. At little higher temperature, little higher temperature, say it is at T2 kelvins temperature, T2 Kelvin temperature, and find another graph which is obtained at T3 kelvins temperature, which is obtained at T2 Kelvin temperature, Now let us identify the highest peak point on the curves. So in this T1 Kelvin, say for example, the highest point on the curve, and in the second curve the highest point, and in the third curve the highest point, noted like this. So now the wavelength of this point so say it is say it is lesser wavelength lambda 1, it is lesser wavelength, still less, that is wavelength increases, lambda 2, and it is lambda 3, wavelength increases. And now here it is, this graph is obtained at T3 kelvins. Okay, T3 kelvins. Now T1 kelvins less than, that is T1 Kelvin temperature less than T2 Kelvin temperature less than T3 Kelvin temperature. Okay, so in this, so wavelength lambda 1 less than lambda 2 less than lambda 3, it increases. So this is intensity increases. So now let us explain the conclusions of the graph once again. So that is the graph plotted between intensity and wavelength of the radiant energy. So now the conclusions of the graph. Okay, so that is, you can expect a theory question from this. important objective questions, theory. Objective theory question you can expect. Right. See this, the height means intensity of the radiation energy. Okay. This height represents what? Along the y-axis. So that shows intensity. Okay. Intensity is less. That means height is less. That is, intensity is less for shorter wavelength light and longer wavelength light. Okay. Should remember that. What is the first point? Intensity of the radiant energy, or you can say radiation energy, is less for shorter wavelength and longer wavelength light. Intensity is less for shorter and longer wavelength light. Okay, that is the first point. And coming to the second point. Intensity of the radiation energy increases. Intensity of the radiation energy increases with increased wavelength. Intensity of the radiation energy increases with increased wavelength. This becomes maximum to certain extent. Then decreases. I repeat the second point again. Intensity means height. Intensity of the radiation energy increases with increased wavelength of the light, becomes maximum to certain extent, then decreases. That is second point. Okay. Coming to the third point. As the temperature increases, T1 less than T2 less than T3. T3 is higher temperature, T2 is still lesser temperature, T1 is still lesser temperature. As the temperature increases, intensity of the radiation energy increases. Third point. As the temperature increases, intensity of the radiation energy increases. That means the height of the graph increases. Coming to the fourth point. At higher temperature. Okay. So at higher temperature means that is at T3 kelvins. At higher temperature. The height of the curve shifted, that is, at higher temperature, the height of the curve increases, no doubt. It is shifted towards left hand side. You can compare all these high points. So that is T1 point, it is T1 temperature, T1 kelvins, the point is identified at this point, and at T2 kelvins, the point is identified at this, and at T3 kelvins, the point is identified. So now, as the temperature increases, the height of the curve increases and shifted towards left hand side. Indicating that intensity of shorter wavelength increases. Okay, that is the important point, all these four conclusions. Okay, so once again let us revise all these 4 points. Okay, so in this, the first point, intensity of the radiation energy is less for shorter wavelength and longer wavelength light. Intensity is less for shorter wavelength and longer wavelength light. Okay, that is understood from the graph. Second point, intensity of the radiant energy increases. The height of the curve increases with increased wavelength of the light. Intensity of the radiant energy increases with increased wavelength, becomes maximum to certain extent, then intensity decreases. Okay, coming to the third point, as the temperature increases, the intensity of the radiation energy increases. Last, at higher temperature, that is at T3 kelvins, at higher temperature, the height of the curve increases and shifted towards left hand side. So for T1, T2 is higher temperature, for T2, T3 is the higher temperature. So at higher temperatures, the peak of the curve shifted towards left hand side, indicating that intensity of the shorter wavelength increases. Okay, suppose if you take only 2 graphs, so we have lambda 1 is less than lambda 2. If you take all the 3, so lambda 1 less than lambda 2 less than lambda 3. So intensity of shorter wavelength increases. That is the conclusions from the graph. Okay, right.